Hello students, in this video we're going to look at Kirchhoff's laws. Now there are two laws that Kirchhoff came up with. The first law, also called the junction law, talks about the current entering or leaving a junction, while the second law talks about the potential changes around the circuit, around the closed circuit. The two laws are very important when it comes to analyzing circuits. When it comes to the first law, Kirchhoff's first law states that at any junction in a circuit, so at any junction point, the sum of all currents entering the junction must be equal to the sum of all currents leaving the junction. If you think about it, this is just a conservation of charge. So if, let's say, you have in a circuit you have a junction at this point, this is where our junction is, and then this splits up such that we have one line going in this direction and we have another line going in this direction. So in this case, we're saying that the current is coming from this side. So we have, let's say, current flowing in this direction. Then it splits up. This is I1. So this side we have I2, and this side we have I3. Let's say I2 is going up like that, and let's say I3 is going down like this. So from the junction law, what we're seeing is that the current entering the junction, I1 is entering the junction. This has to be equal to the sum of the current leaving the junction. So I2 and I3 are leaving the junction. So we end up with I2 plus I3. So if we combine these, we might as well say the current entering the junction is positive. The current leaving the junction comes out as negative. This is equal to 0. So you can conclude that from the junction law, the sum of the current at a junction has to be equal to 0. So this is Kirchhoff's first law, or the junction law. In his second law, he now talks about the voltages, the potential changes around a closed circuit. Now, what it states is that the sum of the changes in potential around any closed path of a circuit must be 0. So, mathematically put, this is what it says. So the sum of the potential changes around a closed path of a circuit must be 0. So what does this imply? Well, for starters, this is just a statement of the conservation of energy. So this is just the conservation of energy. To help you analyze, understand this, let's look at a simple example where we have a simple circuit with one power source, and then we also have one resistor. So let's say we have something like this. The power source is supplying 10 volts, and then this side we have a 5 ohm resistor. To utilize his second law, there are a few key rules that you have to understand, a few key things that you have to understand. Among them, perhaps the most tricky one is when it comes to the potential, the power supply. Well, we're talking about a closed loop here, so it's up to you how you want your loop to really move. But in this case, let's say we take clockwise. So if, let's say, we loop around this circuit in a clockwise manner, so something like this. So what we quickly notice is that when we start, for the power source, here we are moving from the negative terminal, because this is negative, then we're going towards the positive. So here we're moving from negative to positive. And then the other side, we come to pass through our resistor. So in this case, to use the second law, what you have to keep in mind is that if, let's say, we have a power source like this, so if we had a power source, and then in our loop, when looping around this, we decided that we move in this direction. Let's say the loop that we have selected ends up moving from positive to negative. In this case, if this is the setup that you have, then the potential change here is going to be taken as negative, whatever the value is. But if we had the opposite, let's say this, but now we decided, let's say the loop that we selected ends up moving from the negative to the positive. In this case, the potential change across this power source will be taken as a positive value. So positive whatever the supply is. So instead of using E, let me use V. So negative V if we're moving from positive to negative, and positive V if we're moving from negative to positive. What else? Well, suppose in our circuit we have resistors are the other things that you're going to find, the other components that we'll most likely encounter. So if we have a resistor like this, and in our circuit, let's say it is agreed to say, it is taken that current is moving in this direction. So if current is moving in this direction, and our loop gives us something such that when passing through this resistor, we're going in this direction according to our loop. So if this is the case, when looping through a resistor, well, voltage or energy is going to be used up. So the change that will occur through our resistor is going to be a negative change. So the potential change that will arise across the resistor is going to be negative, whatever whatever this is. So across the resistor, the voltage is going to be negative. The drop is going to be a negative drop. So if you know the resistance of this, you can literally just multiply the current passing through this resistor, multiplying the value of the resistance that you have. So, but it has to be negative. But if let's say this is our circuit, this is our resistor, and then in this resistor, current is going in this direction. Current is now going in the backward direction. But our loop, let's say when picking our loop, we ended up with a scenario where the loop is going in this direction. If this is what we have, then the drop that will occur through our resistor, in this case, we'll take it as a positive change. So these are just some of the tricks that you have to keep in your mind when you're trying to apply Kirchhoff's loop law. With these ideas in mind, let's now go back to this example and see how we actually get to use Kirchhoff's second law. Here, since we have a power source, the 10 volts, what we see is, since this is our selected loop, when it comes to the power source, we're moving from negative to positive. So if we use the second law, sum of the voltages, let's see what we find. Let's see if it will give us a 0. Well, here we see that we're moving from negative to positive. So this has to be positive 10 volts. So we're going to have the 10 volts here. But when it comes to the resistor, we know the current will flow from the positive source. So current will go like this. So we expect that the current through this 5 ohm resistor will be flowing downwards. So it's in the correct direction, the same orientation as our loop. So because of that, the drop or the voltage change across our resistor will be a drop. So it will be a negative. And to find it, it will be the current passing through the resistor multiplying that resistance. So how do we find the current passing through the resistor? Well, the voltage from the source is 10 volts. This has to be equal. So of course here I'm using Ohm's law, which is V is equals to IR. So the voltage from the source is 10 volts. Then the current is what I want to find. The resistance itself is 5 ohms. So we see that I, the current, is just equal to 10 divided by 5, which is equal to 2 amps. So with this in mind, you can easily calculate what this sum will give us. So we're going to have 10 volts minus the current, which is 2, multiplying the resistance, which is 5. So you see that we end up with 10 minus 10, which is equal to 0, as stated from the second law. Now let's look at a more general question. What do you expect to find in an assessment, so that you get a better understanding of Kirchhoff's laws? In this example, we want to find the currents I1, I2, and I3. How do we do that? How do we use Kirchhoff's laws to find the currents I1, I2, and I3 in this example? Well, let's start with the first law. From the first law, we see that we have two key junctions here. We have this junction here, B, and we have this junction here, labeled A. So from the junction law, what do we get? Well, from the junction law, at A, what do we have? At A, we're seeing that entering this junction, we have I3. So entering the junction, we have I3. The junction law states that the current entering a circuit, entering a junction, has to be equal to the current leaving the junction. The junction A sees I3 entering, and it sees I1 and I2 leaving. So I3 has to be equal to I1 plus I2. These are the two currents that are leaving. So this is what we get from the junction law at point A. So of course, this can be written as, this is how we're going to use it, but it can also be written as I3 minus I1 plus minus I1 minus I2 equal to 0. But we'll leave it like this. So how about at junction B? Well, at junction B, the junction law, what does it give us? Well, here now, what do we see? The current I2 comes through this line, so it continues through this line, it comes through this, and then it comes like that. While the current I1, the other side, comes like this, passes through that, and then it's coming towards this junction. And then I3 is the one leaving the junction B. So when it comes to junction B, what we see is that entering the junction, we now have I1. Also entering the junction, we have I2. So this is I1 this side, and this is I2 this side. I1 and I2 are now entering the junction, and leaving the junction, we have I3. So if you look at this equation, it's just telling us the same thing that the junction A was telling us, that the current I3 is equal to the current I1 plus I2. So no new information is being obtained here. It's just everything that we know. So let's just label this equation. So let's just label this equation as equation 1. So from the junction law, all that we have obtained is that I3 is equal to I1 plus I2. This is all from the junction law. Now we move on to look at the second law that Kirchhoff gave us. Now from there, of course, let's look at our circuit one more time. We now want to look at the loops and want to look at the changes, the potential changes that occur in each loop. So here we can create up to 3 loops, but let's just see how many we need. So the first loop that we are going to create is going to be just this circuit here. So here it's up to you if you want to go anti-clockwise or clockwise, but for this example, I'll go clockwise. So this is going to be the first loop, and the other side, we're going to create the second loop. And again, we're going to go clockwise. Again, it's up to you if you want to go clockwise or anti-clockwise. So let's say this is going to be our first loop, and this is our second loop. Now, if I split these so that we look at them one at a time, so now it brings us to this one here. So looking at them one at a time, this is now what we have. This is 1 ohm, and the power source here, we're looking at 40 volts. 40 volts the other side too, and then this is 9 ohms. So let's see how it goes. So we selected that we're going to go clockwise like this. So in the first loop, let's see what we're going to get. Using the second law, Kirchhoff's second law, what we're looking at is we want to say the sum of the potential changes in our loop has to be equal to 0 according to his the second law. So let's see how it goes. It's up to you where you want to start from, but here I can start from, let's say I'm going to start from the power source here. So if I start from this, what I notice is here, this is negative, this is positive. So I'm moving from negative to positive if I'm going and if I'm going clockwise. So since I'm moving from negative to positive, remember in this case, for a power source, we'll take it as positive. So this becomes positive 80 volts. Then we find this resistor here. This is a 1 ohm resistor. So for this resistor, the current is moving up this line. So because the current is moving up, of course, we know for resistors, this is going to be a negative change. So this is going to be a negative change. But what is the current passing through this? Well, the current passing through this is this I2 here. This is in series. So I2 passes to the source. It passes through this. So I2 is the current that comes to pass through this 1 ohm resistor. So this is going to be I2 multiplying 1 ohm. So times 1 there. So we continue going up, then we reach the 4 ohm resistor. Current is still going in this direction, the same direction as our loop. So again, this is going to be a negative change since this is a resistor. So this is going to be minus the current passing through that, still I2, multiplying the resistance, which is 4 ohms. And then now we start going downwards. Going down, we're seeing this is a power source, and we're moving from the negative to the positive. Again, from negative to positive for a power source, this is going to be positive. So we're going to have plus the power source, that is a 40 volts. Then we find a resistor. Again, the current is going downwards, same direction as our orientation or as our loop. So this is going to be negative. So this is going to be the current passing through this. Now for this resistor, notice that it's not I2 passing through this. It's now I3. I3 is the one that is passing through this resistor. So it's going to be minus, because it's a resistor, the current passing through it, I3, multiplying the resistance, which is 1, so times 1. Next, we reach 9 ohm resistor, the current passing through this, again, same orientation as our loop, so negative. The current passing through this, that is I3, multiplying the resistance, that is 9 ohms. So this is everything. So this has to be equal to 0 according to Kirchhoff's second law. So we simplify this a little bit. We now have, okay, so this becomes our second equation. So this is coming from the first loop. Now let's look at the second loop. So for the second loop, this is what we're looking at. So try to see if you can come up with an equation, another equation by looking at this loop. So again, for me, for this example, we're taking the loop to be clockwise. So again, you can choose in a direction, but in this case, we are going to maintain the same orientation. We used clockwise here, so we're going to use clockwise here as well. So this is what we have. So it's important that you just maintain one. Once you choose one, stick to it. Okay, so here, of course, we're using clockwise, so try to work it out. And let's see if you're going to find, if we're going to come up with the same equation. Okay, so let's see how we approach it. So again, this is the second law. So we're looking at the sum of the voltages, the changes, and it has to be equal to 0. So for the first part, we're going to start from the power source, the 40 volts. So here, notice that we're moving from positive to negative. Because of our loop here, we're moving from positive to negative. So because of this, the power source is going to be a negative. So again, don't forget, we had this. If you're moving from positive to negative, then the power source here is going to be giving us a negative change. So which is what we are seeing here. We're moving from positive to negative. So because of that, we're going to have negative 40. So the next thing that we find, if we keep on coming like this, we find the 8 ohm resistor. In the 8 ohm resistor, current, this is I1 passing through this. This current is going up. So expect that it's going to go up here. So we're seeing that current is going in the opposite direction to our loop. So because of that, the change that will occur through this resistor will take it as a positive change. If they're going in the same direction, the current through that resistor and our loop, if they're in the same direction, would have taken the drop through the resistor as a negative. But in this case, we'll take it as a positive value. So this is going to be the resistance, 8 ohms, multiplying the current passing through that, which is I1. Next up, from that resistor, we find the 9 ohm resistor. Again, here we're seeing that the current passing through this 9 ohm resistor. This is I3. So I3 is the current passing through the 9 ohm resistor, and our loop is in the opposite direction to that I3. So we're going to have this again as positive. The resistance is 9 ohms. The current passing through it is I3. So current times the resistance, so we have 9 multiplying I3. And lastly, we have the 1 ohm resistor. Again, current is downwards. our loop is upwards, so this is going to be positive again. The resistance, that's 1, multiplying the current passing through that is I3. So this has to be equal to 0. So we simplify this, we have this will remain as 4 I1 plus 5 I3 equal to 20. This becomes our third equation. So now we have come up with 3 equations. Let's just write those 3 equations so that we see how we can work them out. So we have 3 unknowns, I1, I2, and I3, and we have 3 equations, so this should be enough to give us an answer here. So let's see our equations. The first equation was from the junction law, and we had I3 is equal to I1 plus I2 plus I2, just like that. This was our first equation. And then from the first loop, using the Kirchhoff second law, we ended up seeing that 2 I3 plus I2 is equal to 24. This was the second equation. And from the previous scenario, we saw equation 3, and it came out as I1 5 I3 is equal to 20. The only thing that is left now is to work out these 3 equations as a system of equations. So there are different ways you can work out these expressions, but in this example, I'm going to start by substituting I3 into equation 2 and equation 3, and then work out what I'm going to have as a system of equations. So from equation 2, if we substitute the expression for I3, what we end up with is 2, where there's I3, I'll have I1 plus I2 plus I2 is equals to 24. So we simplify this, we have 2 I1 Okay, so this is what we end up with. Then we'll hold on to this as equation 4. Next up, we move on to, we do the same thing with equation 3. We substitute equation 1 into equation 3. And if we do that, what we're going to have is 4 I1 plus 5, where we had I3. We're now going to put I1 plus I2. And this is equal to 20. We simplify. So this becomes equation 5. From here now, we can solve equation 4 and 5 as a system of equations. From equation 4, we have 2 I1 plus 3 I2 is equal to 24. This is equation 4. And then from equation 5, we have 9 I1 plus 5 I2 is equals to 20. This is equation 5. So we can now solve this as a system of equations. To do that, we can use any method again, but let's get equation 4 and let's make I1 the subject of the formula there. If we did that from equation 4, we're going to have 2 I1 equal to 24 minus 3 I2, or I1 will be equal to 24 minus 3 I2 over 2. We can hold on to this as 6. So from here, we can then substitute 6 into equation 5. And let's see what we're going to get. In equation 5, where there is I1, we'll now put 24 minus 3 I2 divided by 2. And then this will be plus 5 I2 equal to 20. From here now, it's just simplification. So this part, we're going to end up with 108 minus 13.5 I2 plus 5 I2 equal to 20. Work this one out for I2. I2 here comes out as 10.35 amps. So this comes out as our value for I2. Once we have found the value for I2, we can go back to equation 6, and equation 6 was an expression for I1 in terms of I2. So this was 24 minus 3 I2 over 2. So since we now know what I2 is, we can substitute, and this becomes 24 minus 3. Where there is I2, we'll now put 10.35. So divided by 2. If we do the math here, we get negative 3.525 amps. So this is what I1 is. Lastly, to get I3, we're going to get equation 1. Equation 1 from the junction law, we had I3 is equal to I1 plus I2. From here, where there is I1, we can put the value for I1, which is minus 3.525, plus where there is I2, the value for I2, we have 10.35. If we do the math here, we get 6.825 amps. There we have it. We have found the values for I1, I2, and I3. If you want, you can actually try them out. You can try to see if you will actually get, if they will satisfy this law. We can try for the first one. We had I3 is equal to I1 plus I2. So meaning we should have I3 minus I1 plus I2. Does this give us 0? Let's try I3. If we try I3, the value for I3, what we have is 6.825 amps minus I1. The value for I1, this is minus 3.525. And then, sorry, this is a negative here. This is a negative, so we have minus here. I2 is 10.35 amps. And if you do the math here, this comes to give you 0, which is in accordance to Kirchhoff's first law. We can try the other equations as well. Do they work as well? We can try them. Equation 2. Equation 2, at one point, to derive it, we had, let's just have the equation first. Let's see which one was equation 2. Okay, so from equation 2, we have 2i3, 2i3 plus I2 minus 24. Let's see, does this give us a 0? So again, substitute the value of I3 and the value of I2. So for I3, we have 6.825. And then for I2, we have minus 24. Again, we see this gives us 0. Lastly, we have 4 I1 plus 5 I3 minus 20. Let's see what we get. Does this give us 0? So we have 4 minus 3, 525 plus 5, 6.825 minus 20. And this gives us 0.025. And this is approximately equal to 0. So this part is just due to rounding off. Okay, so this brings us to the end of this video. So I hope you guys were able to understand how to use Kirchhoff's laws. I tried to make this video or inclusive of the ideas that you need in terms of Kirchhoff's laws. So if you need more examples on this concept, feel free to comment in the chat section, or you can get in touch through email or through my socials. and you can forward me if you've got any questions. All right, guys, we'll see you in the next tutorial.